Okay, good morning. Today we'll discuss photoelectric effect. So, in previous classes, we have discussed it about with the basic uh, phenomena, basic principle conversion of photo energy into electrical energy. Whether you take photodiode, avalanche photodiode, pin diode, solar cell, in these three, the basic principle is conversion of photo, that is photocurrent, into electric current, light energy into electrical energy. And today's topic also same principle. Basic thing what happens in photoelectric effect is photo energy, light energy is converted as electrical energy. Clear? So here in the basic, if you see the heading photo electric effect, photo in the sense light, you know it. Okay, when light is made to incident on few particular metals, example alkali metals, sodium, potassium, cesium, magnesium, etc. If the light is made to incident on these alkali metals, then electrons will be emitted out from the alkali metal. Okay, so that electrons will flow in the circuit. Then that whatever the current that flows in the circuit is photocurrent. Those electrons are photoelectrons. Clear? So this is the basic principle in photoelectric effect. Let us see the construction part here. And this is one electrode, this is another electrode, and in a vacuum chamber we place it. Okay, on this electrode we place a alkali metal. This is alkali metal, sodium, potassium, magnesium, cesium, etc. Here another electrode. Okay, so when a suitable frequency, suitable energy photon incident on this alkali metal, then electrons will be emitted out, right? So if these electrons have sufficient energy, or if you can provide by applying potential difference across it, okay, by applying potential difference across these two electrodes, sufficient potential difference, then these emitted electrons will reach to this electrode. Then you can see current flow in the circuit. You can see the deflection in the ammeter. This is the construction, very simple thing. So here one mathematical equation will discuss, Einstein model, and how photo energy is converted, how this photo energy is utilized, all these things we'll see. Okay, now here in the diagram you see the photon of energy h nu is incident on alkali metal. After taking incidence on alkali metal, that energy is absorbed by electrons. Electron will come out of the metal and moves with some energy, right? So here, what is the incident energy? What is the incident energy? Incident energy is photon energy, right? Light energy, optical energy. This incident energy now is converted as electrons are moving with some velocity. That means what? They will have kinetic energy. So The incident energy converted as kinetic energy of the electron before ejection of electrons, before emission of electrons from the metal. This material or electron consumes some energy to come out of the material, right? So that is called work function. That is called work function. The incident energy is converted as two energies. Part of incident energy is absorbed by the material or electron. That electron utilizes, consumes its energy to come out of the material. Once it comes out of the material, if further has energy, then with that energy, the electron moves with some kinetic energy, with some velocity. Okay, this is according to law of conservation of energy. We can write like this. If we feel there is no loss, and if it is elastic collision, okay, photon collides with electron elastically, total energy of the photon is absorbed by electron and comes out by utilizing some energy, and with the remaining of photon energy, it moves with velocity v. That is kinetic energy. Okay, in that case, the law of conservation of energy is this. Now we'll write formula. What is the energy of the incident photon? H nu. What is the work function? Let us write phi naught itself. Say the electron is moving with velocity v, then kinetic energy is of mv square. M is the mass of the electron. Okay, is this clear? Right. This work function, very important. This work function varies with metals. For example, if you take cesium, for cesium it is 1.9 electron volts. Which one? This work function. And for potassium it is 2.22 electron volts. And for sodium it is 2.3 electron volts. For lithium it is 2.5 electron volts. Okay, the work function of sodium is 2.3 electron volts. Work function of potassium 2.2 like that. Here the work function. What is work function definition? The minimum energy required for the electron to come out of the metal. Minimum energy required for the electron to just come out of the metal. Just comes out. That's all. Further, it doesn't have any energy to travel further. That is work function, right? So this work function depends on metal, not incident frequency, not the intensity of the incident radiation. Clear? The work function depends on metal. It is characteristic property of metal. If metal varies, work function varies. Right? So let us see the equation also for some value for phi naught. So what is phi naught? The minimum energy required. For example, I take a frequency, some frequency nu, so that it has some h nu energy. If that h nu energy is not sufficient, at least to remove electron from the metal. Okay, I'm using some electromagnetic radiation of energy h nu. That h nu value, say less than this value, less than the work function. H nu value less than the work function. Let us assume. Then what happens? Nothing happens, because whatever the energy we are supplying to the electron is not sufficient to come out of the metal. So there is no question of emission of electron. the incident energy also must be sufficient. So you have to supply energy at least minimum, which is equal to the work function phi naught. So we can write phi naught as some photon energy value h nu naught. Okay, so here h nu naught is the work function of the material, or h nu naught is the energy required for electron to come out, to just come out of the metal. That is work function phi naught. Clear? Is it clear? Right. So if you want to have, if you want to make electron to move in towards another electrode, now you should supply more energy. That is higher energy frequencies. You should take and you should incident on the metal. Then it, sum of energy which is equal to its work function will be absorbed. With remaining energy it moves. Is it clear? Let us write that equation with h nu. Okay, so h nu equal to h nu naught plus half mv square. But how to measure velocity of electron in the given experimental setup? Of course, some very good sufficient energies are made to incident on metal, and that electron absorbs, uses this energy, and it will be emitted out of the metal and moving with velocity v, having kinetic energy this. If you want to calculate kinetic energy of the electron, you should know velocity of the electron. How to know how to calculate it? So we should have another way of doing the thing, another way of doing knowing the this value. Okay, in other term, known terms. For that, see here how we are applying the potential difference between these two electrodes. Right here, positive potential is applied, and here we are applying negative potential. Clear? So when electrons are emitted, they move from one direction to other direction. Now we'll reverse the polarity. When you reverse the polarity, instead of electrons moving to that electrode, the electrons will stop in between. Say electrons are moving with some velocity. If you want to stop the electron, if you want to make kinetic energy of the electron zero, you have to apply a opposite potential. It is called retarding potential. You just change the polarity here. Then these electrons will be opposite. Emitted electrons will be opposite. These emitted electrons will not reach to this electrode. So where all these emitted electrons are stopped for the potential for which, the retarding potential or negative potential for which, or simply the potential for which all the electrons are stopped are called retarding potential, stopping potential. Say V naught is the stopping potential, or negative potential. V naught is stopping potential or negative potential. Clear? If the electrons which are moving with velocity v having kinetic energy of mv square, if you want to stop it, you have to apply a energy which is equal to half mv square but in opposite direction. That is what this EV naught, stopping potential energy, retarding potential energy. So mathematically, EV naught should be equal to its kinetic energy of mv square. Now we'll substitute in this equation EV naught. From this, you can calculate whatever they ask. If you want to calculate, if you know incident radiation, you can calculate work function. and this nu naught is called threshold frequency. The minimum frequency required to remove electron from the metal is called minimum frequency of the incident radiation, incident photon. To remove the electron, just remove the electron from the metal is called threshold frequency, and accordingly threshold wavelength also can define. Okay, is it clear? This is the theory what we have discussed here. The photoelectric effect, the what is the phenomena? The phenomena in which when suitable frequency of suitable frequency radiation visible in visible region or UV region, that suitable frequency is made to incident on alkali metals, then electrons will be emitted out from the metal and current flows in the circuit. This phenomena is called as photoelectric effect. So the experimental setup for photoelectric effect is this. This is one electrode, and on that electrode we place alkali metal, and we made to incident some suitable photon radiation. Photon suitable photon is made to incident. Suitable frequency photon is made to incident on alkali metal. Then electron will be emitted out. These electrons are get accelerated using external potential difference. Then electrons reach to opposite electrode. We see the current. Okay, and we applied law of conservation of energy. So the incident energy, incident energy of the photon is equal to the energy required for the electron to come out of just come out of the metal, plus with which it moves with the remaining energy of the photon with which it is moving is its kinetic energy, that is half mv square, and we have calculated the kinetic energy in terms of stopping potential. So finally we got this equation. If you want to calculate how much potential energy is required, if you know stopping potential that we performed in the lab, we know stopping potential and we know incident radiation, then we have calculated stopping potential. That also you can do. Clear? Now let us see another important in the same photoelectric effect. One more important thing is the characteristics of um, characteristics in the photoelectric effect. Right? Just a minute. This in terms of graphs we discuss. First one we'll discuss effect of potential on photoelectric current. Okay. See, this is okay. Excuse. Now, these are very, very important and of course very interesting. Listen carefully. How this is what we are discussing here, effect of potential on photoelectric current. On x-axis we have taken potential, on y-axis we are taking photocurrent. Gradually we are increasing the potential, and here we consider only one metal. Single metal is saying sodium, potassium, whatever, single metal. We are not varying work function, that is we are not varying potential, metal, right? But we are varying different intensities of light. We are increasing the intensity of light. Say for intensity of light I1 initially, okay, even though it's zero potential, if that photon has sufficient energy to even give some kinetic energy to the electron. For that intensity, even though at V equal to 0, some current may be seen, photocurrent. Okay. If you some number of electrons emitted out, few may reach to other opposite electrodes so that you can see current flow. If you increase the potential across these two terminals, see here you can see the diagram. Electrons are emitted, just emitted. Say V is 0. Even though V is 0, some of the electrons may have sufficient energy to reach the this opposite electrode, so that you can see some deflection. That value is this. Is it clear? Now further, if you increase the potential, whatever the electrons that are emitted out will reach to opposite electron. How many electrons are emitted out? Say for that intensity, some 100 electrons, just for example. For that intensity, 100 electrons. For that intensity, for that frequency, 100 electrons are emitted out. So before applying potential difference, only few 10 or 20 electrons are reached because they may have sufficient energy, and these electrons from other regions of the metal may not possess higher sufficient energy to reach that electrode. They will be emitted out, they will travel up to some extent, and their energy gives out to the environment. Okay, they will not move, they will not reach to that electrode. So we are applying potential difference. If you keep on increasing the potential difference, what happens? How many number of electrons are emitted out, that many electrons will reach. See here, for that energy, if you supply energy continuously, same photon if you supply continuously, only 100 electrons will be emitted out for that intensity of light, for that frequency. We are not varying frequency. Okay, frequency of the light is sufficient to emit the electrons. For given intensity, say 100 electrons are emitted out. If you keep that intensity constant, only those 100 electrons will keep on emitting out of the material, will reach to that electrode. See, these only 100 electrons are reaching. That means what? Current flow is constant for that particular intensity of light. Current flow is constant. Even though you increase potential difference very high, maximum, there will be some limit. You keep on increasing the potential, but if you don't increase intensity of light, you cannot fetch out, you cannot remove more number of electrons from the material. For that intensity, there will be some number of electrons that will come out. They will come out if you keep on supplying the photon. That number of electrons for that intensity will come out. Clear? So saturation takes place. That is saturation current maximum. That ammeter will not deflect further. It will be stopped at 10 amperes, for example. It stays over there, 10 amperes. If you supply the photon continuously and if you apply maximum potential difference to accelerate the electrons. Is it clear? Here, for a given single photon energy, for a particular intensity of light, the number of electrons emitted out of the metal is constant. By applying potential difference, you can accelerate only those emitted electrons. You cannot get more number of electrons from the metal for the application of potential difference. That is not true. You can accelerate the emitted electrons by applying potential difference. That's all. Now let us increase the intensity of light. When you increase the intensity of light, you are fetching more number of electrons. You are removing more number of electrons from the metal. Frequency we are not varying. More number of electrons we are getting. Initially say 100. For this I2 frequency, say 200 we got. In that case, few of those 200 electrons even though without application of potential differences at zero potential difference, they may reach to electrode. Due to that, some current we get. Remaining the electrons will not have, remaining electrons do not have sufficient energy. So we accelerate them by applying potential difference. So those electrons will, how many electrons how many electrons will reach to that electrode? How many got emitted out? How many have come from the metal? Only that many. You cannot create new electrons. So saturation current. So keep on increasing the intensity, you magnitude of current increases, okay, but it will have some saturation value. So this is effect of potential on photoelectric current. Clear? Now, interesting thing is this. Now we applied here this region. We increased potential difference to accelerate the electrons. Let us change the polarity. We'll apply retarding potential in opposite direction. Then initially it has some current, no? Initially here some current is there. Clear? Now if you apply retarding potential, the electrons which have sufficient energy to reach this electrode also get opposed, and they will not reach over there, they will be stopped. They will be stopped at a particular value. They are stopped in the sense current becomes zero. See, at a particular value of stopping potential minus V naught, current is zero. Clear? So this minus V naught is independent of minus V naught stopping potential does not depend on intensity of light, right? This depends on, you have to tell, we'll see that. Three more graphs we have to discuss, there you can understand. On what factors stopping potential depends? You see the equation. On what factors stopping potential depends? Okay. If you vary the frequency, does stopping potential vary? Okay, just think of it. Next slide will discuss that also. What is my question? When you increase the energy of the incident radiation, then does stopping potential also vary or constant for a given metal? If you increase the for energy of the incident radiation, what is the value of stopping potential? Does it vary or constant? That is the question. Next we discuss one more point. Effect of intensity of light on photocurrent. So you just think of that question also. You can answer. You can answer in the comment section. Um, does stopping potential depends on what is the value of stopping potential when incident radiation energy is varied? If you keep on increasing the incident photon energy, different energies, if you increase, how stopping potential varies? Does it vary or constant? So Srikar and Pawan Kalyan answering as constant. We'll see it. Okay. Now, this is one more important effect of intensity of light. Effect of intensity of light on photocurrent. In the previous topic, we have discussed effect of potential on current, photoelectric current, effect of potential. Now we are discussing effect of intensity on photocurrent. So intensity of the light is taken on x-axis and photocurrent on y-axis. For a the condition is the whatever the incident radiation should be greater than threshold frequency value. Otherwise, electron will not come out of the material. And we are keeping single frequency value. Mu is constant, and we are using uh, the potential value is constant. Okay, right. So if you keep on increasing the intensity, what happens? We are applying some potential, we are keeping some constant potential so that emitted electrons will reach to electrode. That's all. We are not varying the potential here. That's why Vp is constant. If you keep on increasing the intensity, what happens? Current increases because number of electrons emitted will be more, increases for that frequency. If you for that particular frequency, if you keep on increasing the intensity of the light, more number of electrons emitted out will be increases because you are applying proper potential differences, constant higher potential differences, so that the emitted electron will reach the opposite side, opposite electrode. So if you keep on increasing the intensity, more number of electrons will be increased. Okay, so Neha also saying constant for the previous question. You will see that. Okay, others also can answer it, whether it is constant or varies. And I have given hint also. Stopping potential. What is formula for stopping potential? EV naught of mv square. You just think of it. Okay, so simple it is. As you increase the intensity, current increases. Right. Next, we'll discuss how this one, how the frequency of incident radiation has effect on stopping potential. Now you can answer, I think. Now, what is the point now? How the frequency of the incident radiation affects stopping potential. What is the effect of frequency of incident radiation on stopping potential? Potential is taken on x-axis, photocurrent on y-axis, and saturation current. You can understand what is saturation current for that frequency. For that intensity, number of electrons will be emitted same. So that is the maximum current flown in the circuit for a given intensity of light for a given frequency of incident radiation for the application of potential differences. That is saturation current. Right. Now seeing this graph, three curves are there in this case. Nu1, nu2, nu3. Nu1 is one frequency. Nu2 is another frequency. Nu3 is another frequency of light. Three frequencies we are taking. Nu1 greater than nu2 greater than nu3. Right. For the intensity we are taking constant, maximum intensity we are using. Intensity is constant and metal is constant. Right. Simply what we are varying frequencies. And this nu1, nu2, nu3 is greater than nu naught. Okay, it is greater than threshold frequency. Right. So when light nu1 is incident on the metal, if you apply the potential difference, some current will be flown. And if you apply in opposite direction, it has some stopping potential. Nu1 has some stopping potential. Metal we did not change. New one has some stopping potential. Okay, I'm answering the question. You three are answered as constant. Now you check. Now we varying the this one frequency of the incident radiation nu2. For that it has different stopping. See, stopping potential is what the energy required. Stopping potential. In the previous question also, I think I asked you about stopping potential. This is right. What is stopping potential? The energy required to stop the moving electrons after which are emitted from the photometal. So the moving electrons possess energy. The moving electrons possess energy which is equal to remaining energy of the photon after here. I mean to say, when photon is incident on the material, some of the energy is utilized as work function. So whatever the remaining energy is there, that remaining energy is converted as kinetic energy. If the incident radiation, incident energy, if you keep on increasing for a given single metal, remember, for a given single metal, for example, you take sodium. Sodium has 2.3 electron volts work function. So it utilizes 2.3 electron volts irrespective of the incident radiation. Incident radiation must be greater than this value. Say we applied. For example, the incident radiation, we use 2.5 electron volts. Because we have taken sodium, it has potential, stopping potential 2.3. So what is the remaining energy? What is the remaining energy? 0.2 electron volts. With this remaining energy, electrons moves with some velocities, that is kinetic energy of the electron. Now what is the kinetic energy of the electron? 0.2 electron volts. Now I increase this value, incident radiation. This is incident radiation. Now I am varying this value. I am changing this value to example 5 electron volts. So 5 electron volts incident radiation is made to incident on photometal sodium. What is the energy it absorbs now again to emit the electrons? 2.3 electron volts only. What is the remaining here? If you remove 2.3, if you subtract 2.3 from 5, now the remaining energy has become 2.7 electron volts. In this case, the electrons has 0.2 electron volts kinetic energy. In this case, the electrons has 2.7 electron volts kinetic energy. Now you tell to stop these moving electrons, in which case you should apply more energy. Obviously this. If you want to stop the electrons which are moving with 2.7 electron volts energy, you have to apply this much energy. The electrons which are moving with 0.2 electron volts, you have to apply. So here you should apply less energy to stop the electrons. It requires less stopping potential energy. Here it requires more stopping potential energies. So if you keep on increasing incident radiation energy, if you keep on increasing the energy of the incident radiation, you will get kinetic energy of the electrons also in increasing manner. When kinetic energy of the electrons are increasing, obviously if you want to stop that, you have to apply higher stopping potentials. That's why we have different values of stopping potentials. Clear? So it is not constant. Stopping potential varies with incident radiation. and it does not depend on work function or material. Here, right? Good. I hope it is clear. And one more important thing I want to share with you. Um, actually, if you want to have some discussion on this topic, after this class, I will share a link conference call, one link. It is lightweight and secure because we are using for the other purposes to learn some spiritual things, Bhagavad Gita, etc. That I will share with you. You install it. Okay, join into the call. I will unmute. If anybody has doubt, I will unmute them. You can ask the doubts. We'll discuss. After completion of this session, within 5 minutes, I will share with you. Within 5 or 10 minutes, you join. I will mention the time also. Just we'll have discussion for maximum of 10 minutes. Right. One more important thing. So how threshold already we discussed it. Same thing again, another graph. So it is the how stopping potential is varying with frequency. If you keep on increasing the frequencies, okay, then for different metals, if you take any metal A, it has the same threshold value, threshold frequency. If you keep on increasing frequency, the stopping potential also increases. This is the graph you have. Okay, I think you got some clarity in the photoelectric effect. How how potential is varying, how work function is varying, how intensity with intensity, how these parameters varies. And one more important point you remember, work function. Work function does not depend on incident radiation, frequency of incident radiation, or intensity of incident radiation, or stopping potential applied across. Okay, work function does not depend on. I said again, repeating. Work function does not depend on incident frequency, incident radiation frequency, intensity of incident light, or stopping potential applied. On these three factors, work function does not depend. Work function purely is the characteristic property of the metal we have taken. Sodium, it has some value, 2.3 electron volts. Cesium, it has 2.2 electron volts. 1.9 electron volts. Potassium, 2.2 electron volts. So work function is characteristic property of a metal. It is the property of the material. It does not depend on any other things like these three: frequency, intensity, or stopping potential, or potential difference applied. If you vary metal, stopping potential varies, right? Okay, so this is the photoelectric effect. And one more important, yesterday somebody asked, he did not mention, he or she, student did not mention the name. Student, what is his name? I don't know. See, if you have any questions, you mention the name. Some last digit 7139. I don't know. At least DP also is not there. That student asked the question: is quantum efficiency and conversion efficiency same? In case of solar cell, quantum efficiency and conversion efficiency same or not? Okay, that is the question. So Very good question. Nice. Quantum efficiency is just a number. I mean, for one photon incidence, if that one photon can create one electron hole pair, then the quantum efficiency is 100%. The number is 1. The efficiency is 100%. It doesn't talk about whether the total photon energy is utilized to create electron hole pair or not. That is case of quantum efficiency. So quantum efficiency is the ratio between electrons collected at metal contacts to the number of photons incident. That is the I replied to him or her. So what is conversion efficiency? Conversion efficiency talks about energy. How much energy of the incident radiation, how much photo energy is converted as electrical energy. That is conversion efficiency. Clear? So conversion energy formula is what? How much incident? It is a ratio between maximum power that incident on the solar cell to the power we obtained, we got. The power of the incident radiation to the power of the current we got. In terms of energy, the conversion efficiency talks. Generally, conversion efficiency is less, very less. I think maximum we 60% also. I think we did not reach conversion of light energy into electrical energy. Mm, long back, I've seen it. We'll see. I will check it tomorrow. I can give a clear percentage how much conversion efficiency at present we obtained. We are getting. Okay. So this is the today's topic. And one more important point. Today morning, I shared a Facebook link. In that you can follow it. You just practice in the morning. That yoga practices, simple techniques, eye techniques. If you follow that eye techniques, you can get that eyesight also can slowly you can come to normal project. It depends on you should do. You should have more patience, and you should practice regularly. Do it. Just practice those simple pranayamas, simple exercises, and be fit, be healthy. Don't take junk food. Anyway, you don't have any junk food outside. Okay, and don't take in future also. Don't take bandi, pani puri bandi food. Yesterday I was listening to one discourse. Without that bandi food, పానీపూరి బండి ఉంటుంది కదా బండి ఫుడ్ అది లేదంటే ఈ బండి మన శరీరం అనే బండి నడిచే పరిస్థితిలో లేదు మనకి. మెనీ ఆఫ్ యూ. సో డోంట్ టేక్, స్టే at home, be safe, read very good books, read regular books, prepare for examinations. Okay, soon you have to write exams, prepare for exam. Be happy, stay at home. I'm ending the stream. Good luck.